In the previous class, we looked at depicting the normal shock solution on TS and PV diagrams, and these are the two diagrams that you are looking at. The state 1 here is the state ahead of the normal shock, and state 2 is the state behind the normal shock. This is illustrated on a TS diagram here, and we illustrated the same thing on a PV diagram. Again, state 1 denotes the state ahead of the shock wave, and state 2 denotes the state behind the shock wave. One important aspect about this diagram is that although we have connected states 1 and 2 using a line, you must keep in mind that states 1 and 2 are actually not connected by a line. State 1 and state 2 is a discontinuous solution, so we have a wave. So, for the purposes of illustration, we have connected the two states with a straight line, but notice that the flow actually does not go through any of the intermediate states here. It is a discontinuous solution, so we go directly from state 1 to state 2 without passing through any of the intermediate states. This is very important because the next solution that we are going to look at, for example, flow with heat addition, we will go from a state 1 to a state 2 through many intermediate states, which puts even more restrictions on what is possible and what is not possible. So, I wish to draw the distinction here that we go directly from state 1 to state 2 without going through any of the intermediate states. Okay. What we are going to do next is redraw this PV diagram from a slightly different perspective, which offers us a much more generalized insight into the nature of the flow, so that we can apply the theory not only for a normal shock wave, but for certain other solutions as well. Okay. So, we are basically going to focus on the PV diagram and then redraw it from a different perspective. Okay. Let us see what we can do. So, basically we are continuing our discussion with further insights into the normal shock wave solution. So, if you remember the continuity equation that we had written down earlier, look like this: rho 1 u1 is equal to rho 2 u2. And in fact, I can actually write this as a mass flow rate, say m dot divided by some area A. Okay. Rho 1 u1 is equal to rho 2 u2, which can be written as a mass flow rate divided by area of cross section, and I am going to denote this quantity as G. Okay. Notice here that G is always a positive quantity because we are saying it is mass flow rate divided by a cross sectional area. Right. So, this is our continuity equation, and the momentum equation look like this: P1 plus rho 1 u1 square is equal to P2 plus rho 2 u2 square. And if I substitute for u1 from the continuity equation here, so basically I am going to write u1 as G divided by rho 1. If I do that now, so I do the following substitution: and u2 equal to G divided by rho 2, then the momentum equation becomes P1 plus rho 1 times G square over rho 1 square, that is equal to P2 plus rho 2 G square over rho 2 square. And if I simplify, I get P1 plus where I have used the fact that the specific volume is the reciprocal of the density. Right. So, I have replaced the rho 1 with the specific volume. Rearrange, I can write this as, I am sorry, this is G square, right. There is no G1 or G2, this is G square, and if I rearrange this, I can write this as P1 minus P2 is equal to minus V1 minus V2 times G square, or I can finally write this as P1 minus P2 divided by V1 minus V2 is equal to minus G square. And remember, G is a positive quantity. And let me emphasize that again, G is always greater than 0. So if you think of a PV coordinate space, right, this is the equation to a straight line passing through state points 1 and 2 with a slope which is negative. Remember, G is always positive, so the slope of this line is always negative. So we are going to redraw the, I am going to redraw this PV diagram with a slightly different perspective. Okay, so what is that going to look like? Let us take a look. So let me complete this and say that this is a straight line with slope minus G square in PV coordinates. And this straight line is called the Rayleigh line. Okay, so this straight line is called the let us see what this looks like. So we basically start in the same way as before. Let's say this is my PV space, and let's say P1, let's say this is state point 1, so P1 is given, and let's say that T1 is also given, so let's say that this is T equal to T1, and the isentrope that passes through this point can be shown like this. So this is S1. So let me do this slightly better. So let me write this as state 1, and so now the isentrope that passes through state 1 is given like this. So if I go up this isentrope, let's say up to some point where the, so let's say this is my stagnation temperature. So the isotherm corresponding to T equal to T01 cuts over here. So this corresponds to the stagnation state 0, 1, with this being P 0, 1, right, that is the stagnation state. And this is the, if you, since I know T01, I can calculate T star, and the isotherm corresponding to T star is going to be something like this. So this is the sonic state where m is equal to 1. So we are in this branch where m is greater than 1. We know that m1 is greater than 1. So we are in this part of the line where m is greater than 1. So the initial flow is supersonic. So far this diagram is the same as what we have drawn before. Okay. Now what we want to do is we wish to draw this line. So this line passes, there is a straight line passing through state 1, right, and it has a slope which is always negative. Okay. We do not know where state 2 is, that we will do later. We know that this is a straight line which passes through state 1 with a negative slope. So where can this line be? It must pass through 1 and it must have a negative slope. So any straight line that passes through this can look like this, like this, like this, or like this, right. This has a positive slope and this also has a positive slope. That means this straight line must lie in this quadrant or this quadrant. So I am going to now, this is different from what we did earlier. So I am going to now draw a vertical line passing through state point 1, and now I am going to say that since the straight line passes through both state point 1 and 2 and it has a negative slope, and we know that the line with the negative slope cannot look like this. This tells me that state 2 cannot lie in this quadrant, right, and it also tells me that state 2 cannot lie in this quadrant because the slope is positive. If state 2 lies here, then the straight line would look like this, that has a positive slope. So state 2 is not allowed to be in this quadrant. So let us say that this is a, so that is a forbidden quadrant, state 2 cannot lie there, and similarly state 2 cannot lie in this quadrant also. So these two quadrants are ruled out. So let me just now we are left with two choices. The line can either be in this second state can be here, or second state can be here starting with this state. Now if the second state lies here, let us say that state 2 is something like this. If this is, let us say, state 2, this is state 1, right, this is state 1, this is state 2. What can we say about P1 and P2 and V2 in comparison to P1 and V1? P2 is less, V2 is more. So that means this is an expansion shock solution, which as you know is forbidden by second law of thermodynamics, because the entropy for this point would actually be less than the entropy here. Any solution which lies in this quadrant will have S2 less than S1. So solutions which lie here are also forbidden by second law, right? They are forbidden, but they are forbidden by second law. So any solution, any state point 2 that lies here is not allowed, because any solution here represents an expansion shock wave with S2 less than S1, which is not permitted, which means that state 2 can lie only in this quadrant. Is that clear? So let us draw a line. Let me draw a line. So this is a line with slope minus g square. So starting from this, state 2 must lie somewhere along this line. We do not know where it has to lie, we will determine that next. So this is the Rayleigh line, okay. Now we go to the energy equation. We have made use of the momentum equation. We next go to the energy equation to see what we can do with it and to locate state 2. So the energy equation, if you remember, was H1 plus so we substitute for U1 and U2 in the same way as before, and we end up with now if you rearrange this and do a little bit of algebraic manipulation, we can finally end up with an equation that looks like this. I am not going to derive this in detail here, it is available in the textbook, but if you go through a little bit of algebra, you can finally show that this can be written as now this is actually a quadratic equation in PV coordinates. If I replace the P2 with a P, I can show that this is a quadratic equation in PV coordinates, and notice that it passes through state points 1 and 2. So the actual state 2, we said that state 2 can lie anywhere along this line. The actual state 2 must then lie at the point of intersection of this straight line and this quadratic, right. This is a quadratic which passes through state point 1 and 2. This is a straight line which passes through state points 1 and 2. So state point 1 lies at the intersection of this quadratic and the straight line. State point 2 also lies at the intersection of this quadratic and this straight line, right. So let us draw the quadratic and then see what this looks like. This quadratic is also called the H curve. I am going to try to draw the quadratic here, but if I am not successful, we will actually look at the figure. Okay. So this is the H curve. So notice that this was state 1. So point of intersection of the straight line with this H curve, state 1. Point of intersection of the H curve with straight line and H curve gives me state 2. So this is state 1, this is state 2. Okay. Notice that there is also a point of intersection on this side. If this is another Rayleigh line, you will get another state point 2 here, but as we said earlier, this solution is not allowed by second law of thermodynamics. Yeah, go ahead.
So that 2 points should lie below stagnation point, stagnation
temperature. Yeah, no, I will show this picture much more clearly in the diagram. Okay, this is the best I can draw on the board. We will look at this on the monitor here. So this is what the solution looks like. So you can see the features that we already discussed. So this is state point 1, right? And you see the Rayleigh line, which is the straight line here on this side, and the Rayleigh line, which is the straight line on this side. And states, downstream states 2 are not, state 2 is not allowed to lie in this quadrant or in this quadrant, as we discussed earlier. And it can actually lie in this quadrant, but such a solution would imply S2 less than S1. So we do not allow the solution to lie in this quadrant also. So the only possibility is for the state point 2 to lie in this quadrant. And now if you draw the H curve which passes through state points 1 and 2, which looks like this, you can see that this point of intersection gives me the downstream solution. Once again, you must keep in mind that we do not go from state 1 to state 2, we jump from state 1 to state 2. This is an extremely important fact which will become very clear to you when we go to the next chapter. Okay. Please bear in mind that we do not go from 1 to 2 through the intermediate states, we directly jump from state 1 to state 2, which means that we need not pass through any of the intermediate states. Okay. So as you rightly said, you can see that state point 2 lies below the stagnation isotherm, and once again if I draw S equal to constant here, this is my where it intersects the isotherm T equal to T naught, gives me my stagnation state 0, 2. So this is P0, 2, and as you can see P02 is less than P01. Notice also that the H curve that is drawn here is steeper than the isentrope that passes through state point 2 or the isentrope that passes through state point 1. Because this is steeper than the isentrope, for a given change in specific volume, the compression using normal shock is more effective than compression using an isentropic process. Because the H curve is steeper than the isentrope, for a given change in specific volume, I get less pressure in my isentropic compression and more pressure in my normal shock compression because of that. Okay, we demonstrated this the other day. Let us just write it down in words and go on. So let us say that this is state point 1, and let us say that this is the isentrope which passes through state point 1. Now remember, the H curve is actually steeper than, so this is state point 2 and this is the H curve. Since the H curve is steeper than the isentrope, since it is steeper, for a given change in specific volume V1 minus V2, the change in pressure, this is P1, this is P2. Had we compressed using an isentropic process, we would have remained on this S equal to S1, so I would have come up to here. So this is the pressure rise, let me call this 2S, so this is the pressure rise that I would have seen if we had compressed isentropically, but since the H curve is steeper, for the same change in specific volume, I get much more compression. Okay, we discussed this earlier, now we are seeing this once again with the H curve also. Okay, remember what we have drawn here, this is the H curve that corresponds to an adiabatic process, so I am going to put it down as H Q equal to 0. Remember when we wrote down the energy equation, we said that the process was adiabatic, so this is the H curve corresponding to Q equal to 0. Okay, any questions? Now this theory will be very useful when we go to the next chapter where we are going to look at flow with heat addition, especially this point about jumping from state 1 to state 2 without going through any of the intermediate states is very important, because if you have to go through the intermediate states, then you end up with a limiting condition called thermal choking, which is not there for the normal shock wave because it is a discontinuous solution. I can go from here to there, we will discuss that next. The next chapter that we are going to look at is flow with heat addition. Which is also known as Rayleigh flow. The theory that we are going to discuss here applies whether you are adding heat to a flow or removing heat from a flow. Both are okay, but removing heat from a flow is very rarely seen in a real life application. Okay, whereas addition of heat to a flow is seen very commonly in combustors, right. So we talked about combustors, and what are the combustors that we are talking about? So we are talking about, for example, aviation gas turbine combustors. That is our interest in this course, aviation gas turbine combustor or a ramjet combustor or even a scramjet combustor. These are the types of combustors that we are talking about, where we add heat to the flow, and what we want to know is if compressibility effects are significant, then what happens to state points, how do things change when we add heat to the flow. So we already mentioned in the very early part of our course that in the case of a gas turbine, aviation gas turbine engine, insofar as the combustor is concerned, compressibility effects were largely absent. In fact, we will now show mathematically why that is so. Okay, that is something that we will do. So given this, the primary interest is in flow with heat addition. We very rarely require heat removal, okay, although the theory applies equally well. That is our interest. So let us write down the governing equations for such a flow. The governing equations are the same. one dimensional flow equation. So, we are looking at a scenario which looks like this. So, let us say that this is my combustor. So, it is a constant area combustor, right. So, it is a constant area combustor, flow comes in, let us call this state 1, flow goes out, let us call this state 2, and we add heat to the flow here. And we want to know if I add a certain amount of heat and I have a flow coming in at a certain condition, what is going to be the outlet condition. Okay. In other words, if for example the flow comes in at a pressure P1, temperature T1 and velocity U1, and let us say stagnation conditions T01 and P01, what are the exit conditions going to be like. So, we want to know say P2, T2, U2, P02 and T02 for a given value of Q. That is what we are trying to find out in this particular chapter. So, the governing equation, so you can see that because the area is constant, there is only one velocity component, so it is one dimensional flow. So, the governing equations are almost the same as before with a small modification because we are adding heat to the flow now. So, the continuity equation looks the same, momentum equation looks the same, energy equation looks almost the same. So, notice that I have now included a heat addition term here. This is heat added per unit mass or unit mass flow rate, if you will. Okay. Apart from this, the earlier calculations we assumed Q to be 0. Now, Q is not 0, Q can be positive, which means heat is added. So, the sign convention is the same as in engineering thermodynamics. If Q is greater than 0, heat is added, and if Q is less than 0, then we are removing heat from the flow. And we supplement this with the entropy equation. So, S2 minus S1 is equal to CV natural log P2 over P1 plus Cp natural log V2 over V1. One important thing that you should realize is that this is not a discontinuous solution that we are seeking. So, the flow enters at state 1, it goes through all the intermediate states before it reaches state 2, correct. So, this is not a wave solution, this is a continuous solution. Okay. So, our strategy is going to be, if it enters with this at this state and I add a small amount of heat delta Q, what will be the change of state? Then if I add another delta Q, what is the change of state? So, I keep adding delta Q like this until I reach the exit. Then I can draw the process diagram on TS or PV coordinates as I like, right. That is going to be our strategy. Now, if you look at the energy equation, okay, notice that I can rewrite the energy equation like this. If I write it as T2 plus U2 square over 2 Cp minus T1 plus U1 square over 2 Cp is equal to Q over Cp. So, I have simply rewritten the energy equation here, and you should recognize that this is T02 and this is T01. So, the addition of heat results in change of stagnation temperature. So, which means that T02 minus T01 is equal to Q over Cp. So, this is also different from the earlier solutions that we saw, because in all the earlier solutions, since Q was 0, the stagnation temperature was constant. Now, because Q is not 0, stagnation temperature changes from one point to another. And remember, if stagnation temperature keeps changing, then T star will also keep changing from point to point. That is something that you should keep in mind. So, what we can see here is that heat addition, wherein Q is greater than 0, increases T naught, and heat removal so if I add heat to a flow, the stagnation temperature increases. If I remove heat from the flow, stagnation temperature decreases. So what we are going to do next is, how do we illustrate the process that the fluid undergoes on a TS diagram? That is what we are going to illustrate next. So our strategy will be, we start from this state, we add a small amount of heat delta Q to the flow, and then we see where the next state is. Then we continue going like this to go from 1 to 2. That is going to be our strategy. So for this purpose, this form of the governing equation is not useful, right? We need the differential form of the governing equations, which we have already written down earlier. So that is what we are going to use. So we will start with the differential form of the governing equation in order to do this. So we will illustrate So if you remember, the differential form of the continuity equation was d of rho u equal to 0, right, from which I can write d rho over rho equal to minus du over u. Okay. The differential form of the momentum equation look like this. And if I rewrite this, I can write this like this. Now, if I use the equation of state, I can rewrite the rho here as P over RT, and if I use the definition of Mach number, I can write U square equal to m square times gamma RT. So this allows me to rewrite this equation as dP over P is equal to minus gamma m square times du over u. Now from the equation of state, I can, since P equal to rho RT, if I take the total differential of this, I can write this as dP equal to R times rho dt plus T times d rho and if I rearrange this, I get dt equal to 1 over rho r times dP minus T over rho times d rho, and now I can substitute for dP from here and I can substitute for d rho from here, and if I substitute for dP from there and d rho from here, I end up with the following. So substitute for dP and d rho, we get dt over T is equal to 1 minus gamma m square times du over u. By now you must see the pattern in which we are developing the equation. Notice that we wrote d rho over rho as in terms of du over u. We wrote dp over p in terms of du over u involving only the Mach number. Now we have written dt over t also in terms of du over u involving only the Mach number. We will continue to do this for all the variables. So we have used the continuity equation, we have used the momentum equation, and we have used the we have not used the energy equation so far. Let us proceed with the entropy equation. So we had ds equal to Cv times dp over p, and if I rewrite the dv over v in terms of d rho over rho, I can easily write it like this. It is not difficult to do this, right? We use the fact that V is equal to 1 over the density, and if I substitute for dp over p and d rho over rho from the previous equations, I can easily show this to be ds equal to Cv times gamma times 1 minus m square times du over u. Now we use the definition of the stagnation temperature T naught. If you remember, since the stagnation temperature T naught is equal to static temperature plus u square over 2 Cp, I can write this in differential form. If I differentiate, I get dt naught equal to dt plus 1 over Cp times u du, and if I substitute for dt and du from the earlier equation, I can write this as dt naught is equal to 1 minus m square times t times du over u. But if you look at the way we have been writing the expression, notice that on the right hand side we want to involve du over u and m. Those are the only two quantities we want, so we would really not prefer to have something like this. So we would prefer to replace this with a T naught, because we have a dt naught here. We would prefer to have this with a dt naught, and I know that since T naught is equal to T times 1 plus gamma minus 1 over 2 times m square, I can rewrite this as dt naught over T naught is equal to 1 minus m square divided by 1 plus gamma minus 1 over 2 times m square times du over u. Okay. Now the right hand side involves du over u and the Mach number. Okay. So we need one equation which determines the change in Mach number dm, right. So we need one equation for that, and that we can get from the definition of Mach number. So m is equal to u over square root of gamma RT, and if I take the derivative of this, right, I can write dm is equal to m times du over u minus m over 2 times dt over t. Now once again substitute for du over u and dt over t from before. This gives me dm over m is equal to 1 plus gamma m square over 2 times du over u. So the nice thing is, what we have done is, for an incremental change in du, I know how to calculate the changes, right. I know how to calculate d rho, I know how to calculate dp, I know how to calculate dt, I know how to calculate dt naught from here, right. I know how to calculate dt naught, I know how to calculate ds and dm. The only problem is everything involves a change in du. If I know the change in du, I can calculate all these other things. But this is a problem where we are looking at flow with heat addition. So what I want to know is, if I add delta Q, right, what is the change in the state? So I would prefer to have delta Q or something related to that rather than du over u. Right. So let us label these equations with an asterisk to show that we are going to, these are the governing equations. So this is one equation which I am going to denote with a star. This is another equation which I am going to denote with a star, right. The third equation is this, and this, and this. So these are the equations that I am looking at. I would just like to involve a delta Q in these equations rather than a du. That is the that's the only thing that I am going to do next. So we would prefer to eliminate du in favor of delta Q, right. So basically what we are trying to do here is like this. Let me redraw the diagram that we drew earlier. So this is state 1, this is state 1, this is state 2, and the flow comes in at state 1, and let us say that I look at an incremental amount of heat that is being added here, delta Q. So when I add an incremental amount of heat delta Q, how does the state change from 1 to a new state? So that means in the new state, pressure is going to be P1 plus dP, temperature is going to be T1 plus dt. But I already have equations that tell me the change. I have d rho, I have dP, dt, and so on. Okay? I just want to relate those changes to delta Q rather than du. That is what we are looking for. Now let us see how we do this. If you remember, earlier we showed that T02 minus T01 is equal to Q over Cp was something that we derived earlier. Now if I take a differential of this, this tells me that dt naught is equal to delta Q over Cp, right. I am sorry, dt naught is equal to delta Q over Cp. So I can either involve delta Q or I can write everything in terms of dt naught. Dt naught and delta Q are the same, right. There is no problem. So what I am going to do is rewrite or eliminate du in favor of dt naught. Right. So what I am going to do is I am going to use this equation here, right, to eliminate du in favor of dt naught. So I will substitute for du in terms of dt naught in all the other equations, and then I am at the point where I want to be. I know how to calculate the incremental change in the properties starting from state 1. If you do that for each one of these starred equation, the resulting equations will look like this. I get d rho over rho is equal to so when the stagnation temperature changes by this amount dT naught, which is the result of an addition of heat which is delta Q, the density changes by this much. Okay. Similarly, dP over P is equal to minus gamma m square times 1 plus gamma minus 1 over 2 times m square divided by 1 minus m square times dt naught over T naught. So, this is how much the pressure changes as a result of an addition of heat which is delta Q, right. And now I can look at change in static temperature, dT over T is equal to 1 minus gamma m square times 1 plus gamma minus 1 over 2 times m square divided by 1 minus m square times dt naught over T naught. Entropy change ds equal to Cv gamma times 1 plus gamma minus 1 over 2 times m square times dt naught over T naught, and then du over u is equal to 1 plus and dm over m Now the equations are in the form in which I want them. I can calculate for a given addition of heat delta Q, I can calculate change in density, I can calculate change in pressure, change in temperature, entropy, velocity and Mach number. Okay. So, this is exactly in the form in which I want these equations. So, what we are going to do next is for heat addition or heat removal in the flow, we are going to try to see how the state point moves from state 1, how does it move on a TS diagram, which way does it go. So, we will track the continuous state. So, basically as I said earlier, so we start with state 1, right, and we look at say an addition of delta Q here, and so starting from state 1 we move to this state, then again we look at an addition of delta Q and we track this state. So, starting from here we track these intermediate states until we reach state 2 and we will plot this process on a TS diagram, right. That is what we will do in the next class.